Uh, Good morning, one and all. Thank you for giving me this opportunity for participating in this great VSSP program and presenting my topic. Today, I'll be navigating you all through the basics of arithmetic functions uh, from sequences to Dirichlet convolution. So, the main aim of this presentation or discussion is that I will introduce the basics of few number theoretic functions and then introduce what Dirichlet multiplication or convolution is, and then we will conclude with some examples. Okay? Yeah. So let us consider a sequence 2, 1, 3, 4, 7. This is a random sequence. So first, let's make it clear what a sequence is. It's a rule assigning to every natural number a to a. So basically, it's a function from natural number to real numbers or complex. So yes, so hence such a real or a complex function, when it is mapped to positive integers, then we call such functions as arithmetic functions or a number theoretic function. Can you name a few arithmetic functions? One or two I have given already. One is the divisor function, other is the summation sigma function. One counts the number of divisors, other counts the sum of all those positive divisors. Yeah. So, can anyone volunteer and then say a few number arithmetic functions that you have familiar with? All right. Okay. So these are all few arithmetic functions or number theoretic functions. Um, yeah. So what does this? We call it as Euler-Torsion function. This is phi. So what does this function do? This function basically counts the number of co-prime numbers that are less than n, less than or equal to n, basically. So this function is called the Mobius function, and this is the constant one function. So we will discuss these things right now. These things follows now. So let us consider Mobius function and Euler-Torsion function for primarily right now. What is Mobius function? It is defined as follows. Mobius function mu is defined as, for mu of 1, it is 1. So what if the n is greater than 1? It can be decomposed into various into its prime factorization, where we define as mu of n is equal to minus 1 to the power k if a1 equal to a2 equal to all ak is equal to 1. What if any of the a1 is greater than 1? Then mu of n becomes 0. Okay. So basically what is happening is that, what is the role of this Mobius function? It is behaving as the detector of square free numbers. So whenever we have a square free number, then we have positive non-zero mu of n value. Okay. Yeah. So here are a few examples. So for mu of 1, it is 1, as we see before. For mu of 2, it can be written in the prime factorization method 2 power 1. So a1 equal to 1. So only k which is there is only 1. So mu of 2 is equal to minus 1 to the power 1, which is minus 1. Okay. So one can compute similarly from 1 to 10 in this way. Now, so we saw the Euler-Torsion function above. Let's see what it is. So if n is greater than or equal to 1, the Euler-Torsion function is defined to be the number of positive integers not exceeding n, which are relatively prime to n. That is basically the co-prime numbers that is less than or equal to n. Obviously, GCD of n and n is going to be n, so it is strictly less than n. Okay, so what is this representation? Phi of n equal to summation k equal to 1 to n dash 1. What does that dash over there means? One can intuitively understand in this way. Suppose we are programming, if true, return 1, else return 0. So in that way, if we are running through the numbers which are less than n, and if any number is relatively prime to n, then give me 1. If not, return 0. In this way, if I count the number of ones which I am getting out of that, that is going to be the number of relatively prime numbers less than n. That is the Euler-Phi function phi of n. So this is just the sum that is extended over those k which are relatively prime to n. Example: suppose if n is 1, obviously phi of 1 is 1 because uh, it is relatively prime to itself. One GCD of 1 and 1 is 1. Similarly, for 2, only 1 is there. So one can easily compute this phi of n for smaller numbers. There is a problem with computing for larger numbers because it is based on the prime factorization. How? Below. So we define this is the general formula for Euler-Phi function computing phi of n. Phi of n is equal to n into this is product p all the primes which divides n 1 minus 1 by p. So this basically depends on the prime factorization of the n. So as we know, for given any large n, very big large n, it is very hard. It's still a hard. It's still an open problem to how to find the prime factorization. So as computing Euler-Torsion function is depending on that. So phi of n computation for large n is still harder. Okay. So this phi of n is not completely not new or unfamiliar with us because we have seen this phi of n in group theory somewhere where this group in group theory we have studied about the unit group u of n where it considers all the k that is relatively prime to n. So what is the cardinality of u of n? That is nothing but the Euler-Phi function phi of n. Okay. So we have read this Euler-Phi function in group theory also. Yeah. Okay. So now let f and g be two arithmetic functions. Okay. So what happens if we add or multiply two arithmetic functions pointwise? This is basically a very intuitive uh, map that we going to define. Uh, f of f plus g of n equal to f of n plus g of n. Similarly, f g of n equal to f of n into g of n. This is the intuitive way of how we define the addition pointwise. This is how we define. So commutativity holds. Why? Because it is inherited from the real multiplication or real addition in this sense. Okay. Similarly, associativity also. Identity under multiplication, we have constant function which is going to be 1. So this is holding true. So now the question is that in addition wise, it is an abelian group. Whereas in multiplication wise, the question arises whether inverse exists or not. Can anyone guess whether this is true or not? Random guess is fine. All right. Okay. So one second. Yeah. So in addition wise, it is an abelian group. In multiplication wise, the problem arises whether every function has an inverse here. No, because if f of n is equal to 0 for some n, then 1 by f of n does not it doesn't exist. Am I clear? Yeah. So in this way, we can't talk about the inverse in this kind of multiplication if we define the uh, if we define this map in this way. Okay. How can we? Okay, can we define a multiplication which respects this divisor structure of integers? So what I want is that I have to somehow I'm in search of a map which includes this inverse property also. So there comes a Dirichlet convolution method or Dirichlet product method. Okay. So there we do a small mutation to this the previous map what we saw in this way. F composition F convolution G. Right now let us call it as star. So F star G of n is equal to summation D divides n f of D G of n by D, where D is the divisor of n. This is how we define a Dirichlet convolution or the Dirichlet product. Okay. Okay. So let's test this on our example. Suppose u of n is equal to 1 for all n. Okay. This is this is what this is what we already know. U of n is equal to 1 for all n. So what is u star u of n? It's going to be summation d of n 1 multiplied with 1, which is going to be all the divisors. I mean, if this is again, one can see it as a computational way. If if I get a divisor in the numbers which is less than n, then return me 1. If not, then pass on. So in that way, the number of ones that is going to give me is nothing but the total divisors that I'm going to get. So u star u is going to give me the total number of positive divisors. Okay. So the divisor function just appeared from the simplest possible function, that is u. Okay, constant function. In a similar way, so what intuitively one question that we can that would arise is that, for example, we saw about sigma function, also the summation function. Let's see if some other function which we know is going to give me that sigma function in this following way. So what about, let's call this identity function as n of n equal to n. Okay, so what is u star n of n? Basically, ID or whatever. U star n of n is nothing but u of d is going to be 1 always, as we know, and n of n by d is n by d. So what n by d is nothing but d, because as it is running from 1 to n by d is same as counting the number of d's. So d divides n summation d is going to give me all the divisors of n. So that is going to be the summation function. So what we saw is, for d of n, for the number of positive divisors, we do u star u of n. For summation, u star n of n. So one should, kind of, one should actually feel how beautiful this is, because when we started with this digital multiplication and defined for some purpose, but this is actually fetching lot of interesting results that we did not expect through this convolution. So one such, there is connection between. Uh, uh, so basically, we are exposing the connections between the constant function and divisor function, constant function and some sigma function. In the same way, one can explore the interesting connection below. That is, phi of n is equal to summation mu of d n by d, where d is a divisor, d divides n. Okay. So I wish to the proof which is given in the postal is a very beautiful proof. I want to do that, but as I don't have much of a time to, if I start doing that, so I request the audience to kindly refer to the Apostle chapter 2 for that proof. It's I'm telling you, it's a very such an interesting proof. One should definitely read it. Okay. So great. So the Dirichlet convolution ties together all these familiar functions. Okay. So now we change the multiplication to Dirichlet multiplication for some goal. Whether have we achieved it? I mean, we are achieving lot of interesting results in the way we are reaching our goal. But whether inverses is respected under Dirichlet multiplication was our initial goal. So yes, let's consider this one example first. Yeah, the Mobius function mu of n is so one can do the u star mu and get I of n. Okay, it's left to you guys as an exercise. Probably it is easily verifiable. Okay, so u star mu of n is going to give me the I of n, where I of n is nothing but 1 by n. If n is equal to 1, then the floor function is going to give me a 1, else it is 0, right? Yeah. So mu acts as the inverse of 1 under convolution, because f star I of n equal to I star f of n equal to f of n. That is Now consider u as some function f, mu as some function f, some function g of n. Okay, so f star g of n is going to give me the identity means g is technically, intuitively at least, g is the inverse of f and f is the inverse of mu. So these can be proved in the upcoming slides, but this initially what we see is mu is equal to u inverse and mu inverse is equal to u. Okay. Uh, some algebraic properties. Uh, Dirichlet multiplication is commutative. Why? I mean, the answer is also here. Fine. So, uh, why is this true basically? Because when I am doing summation f of a g of b, what is happening is that this is completely running through all the positive integers whose product is going to be n. So it doesn't, it is basically indifferent even if I change. It is going to fetch me the complete g f of f star g is going to give me g star f, because if in the starting which was there is going to give, is going to be some other thing which is of some element of g star f. Hope I am clear in what I am expressing. Yeah. So F star G star K associativity basically. F star G star K is nothing but F star G star K. So consider A as G star K and then do summation F of A of D. Then expand A in the inner summation, and now you can get the now you'll get ABC equal to N. From this, now shrink the FA of A and G of B, then we will get our acquired F star of G star K. Right? Okay. So identity. I star F is equal to F star I, which is equal to F. How? F star I of N is equal to summation T divides N, F of D, I of N comma N by D. I of n by d is going to be the floor function of d by n, because I of n is nothing but floor function of 1 by n. So n by d changes to d by n. So this is going to be f of n, because d by n is going to be 0, and only for n only you will get the value, rest of everything will become 0 if d is less than n, right? Okay. So now these properties are being checked right now. Again, we'll see the inverse one. Let f is an arithmetic function such that f of 1 is not equal to 0. Then there is a unique arithmetical function f inverse, which is called the Dirichlet inverse of f, such that f star f inverse is equal to f inverse star f, which is equal to identity. How do we define this? Basically is that f star is given by the recursion formula of this kind. Just have a um, glance at this before I start explaining what this is. Take a minute to um, you know chew this. Take 10 seconds. Yeah. Okay. So let me continue. So f inverse of 1 is equal to 1 by f of 1. For n greater than 1, f inverse of n is going to be this recursion relation which is being mentioned. Okay. So how do we show this and what is this? So basically f star f inverse of 1, if you expand through the Dirichlet convolution method, you will get I of 1. That is f of 1 multiplied with f inverse of 1 is giving me 1, means in as f of 1 is not 0, there is only one solution. F inverse of 1 equal to 1 by f of 1. Suppose we'll see why f of 1 is not 0 also. Okay. Suppose f inverse of k have been uniquely determined for all k greater than n, then we have to solve the equation f star f inverse of n is equal to I of n basically. Now as I said, we will expand it. After expanding, consider d equal to 1, d equal to n. Then and then d less than n. Two cases. First is f of 1 f inverse of n. Rest is this relation which is being there. So if you know if the values of f inverse of t are known for all devices of t less than n, there is a uniquely determined value for f inverse of n. So this demands our knowledge of uh, knowing the f inverse of t for all devices through. Yeah. So then this is nothing but the, because this will go this minus one. This is one. So this will go that side and become minus one, and minus one by f of one will be fetching us this relation. Okay. Yeah. So now let's consider set S, that is set of all arithmetic functions. Then S plus star, that is this, and I mean under these two binary operations, under pointwise addition and Dirichlet convolutions, form a commutative ring with unity. Because under addition we already saw it is be giving me a abelian group. Now with this we checked associativity, and this inverse also. Okay, so hence this is going to be a very specific and special um, um, algebraic properties this is having. So Mobius inversion form. Let's move on to Mobius inversion formula. This is this Mobius inversion formula is very highly useful analytic number theoretic tool. For example, if we consider the very famous Dirichlet series and Riemann zeta function also, it helps us by removing the zeta factor from, if f and g are two Dirichlet series, then it helps us to take the zeta factor out from f and g, where f of n equal to zeta factor of n into g of n. So this is very important and useful formula. How do we define that? F of n is equal to summation g of d divides n. This is if and only if g of n is equal to summation d divides n f of d mu of n comma d. Okay, so how do we prove this? This is very simple and interesting relation. This is nothing but g star u, where u of n is equal to 1, right? So f is equal to g star u, multiply both LHS and RHS with mu, then what we get is, yeah, right hand side becomes g star u star mu, because this is associative. So this is nothing but g star I, which is going to be g, because we already saw u and mu are inverse of each other. U is inverse of mu and the vice versa too. So we have yeah.
Venkat,
Yes sir.
let's try to wind up couple of minutes.
Okay sir. Okay, yeah. So with f star mu is equal to g, one can prove in the conversely also that f is equal to g star mu in a similar way by multiplying in the with mu in the left and right hand side. So from this Mobius inversion formula, we can get n is equal to summation t divides n phi of d, and phi of n is equal to summation mu of d n by d. Okay, so I mean this is some lighter note about multiplicative functions. If f of m comma m f of mn equal to f of m into f of n, then GCD of m and n is 1. Similarly, we can define completely multiplicative for any m and n in Z, f of mn equal to f of m into f of n. So here are some examples which are being given for both cases. So are multiplicative functions closed under Dirichlet convolution? Yes, of course, because if f and g are multiplicative, then f star g is also multiplicative. And as a later note, hint is being given to how to prove this. One can have a look at that. For multiplicative functions, what must f of 1 be? Because GCD of 1 and 1 is always 1. F of 1 equal to f of 1 the whole square. From this, we get f of 1 equal to 0 or 1. When is f of 0? If f of 1 is 0, then we can say f is congruent to 0. Otherwise, f of 1 equal to 1. And this is true for any non-trivial multiplicative function. Okay? So overall picture of what we saw is that operation when it is pointwise, identity is u of n. Inverse condition is this. For Dirichlet convolution, identity is I of n. F of 1 is not equal to 1. For any multiplicative subclass, for example, the completely multiplicative or the normal multiplicative, identity is I of n. Inverse condition is f of 1. So just a take home question for everybody is that, so changing the operation from pointwise to convolution, our world of arithmetic function became a rich abelian group. Moreover, a commutative ring with inverse. So now we define another operation using some Dirichlet series. We mutated a normal multiplication and got Dirichlet convolution. In the same way, if we mutate in some other way, how do these algebraic properties reflect in analytic ones? So this is a very interesting question, and one can explore a lot from this. I request the audience to chew this in their free time. Okay. Thank you very much.